Now we are going to prove a necessary and sufficient condition for a bounded function defined on closed interval AB to be Riemann integrable. Means necessary and sufficient condition. But what we do is, before proving the main result, we will quickly revise the important concepts, or the concepts or basic concepts, which are necessary to study this theorem. And also, before proving the actual result, we need one more theorem, that is Darboux's theorem, which will be used to prove the main result, that is necessary and sufficient condition for a bounded function to be Riemann integrable. Let us start with basics. Let us recollect whatever we have learned in this chapter. So first of all, to discuss integral a to b f of x dx. First thing we need is f of x should be a bounded function. What is this? F of x is a bounded function on closed interval a. That means f of x has infimum and supremum on closed interval a. Right, this is the first point. Second one, we defined partition P, partition of AB, right? So what is partition? Partition is nothing but a set of points between A and B. Set of points between A and B. Right. So A is treated as x0 and then x1, x2 and so on, in between general points xr minus 1, xr. Of course they are increasing. And so on. Xn minus 1 and xn. So like this we have set of some points between A and B, including A and B. That is called partition. And set of all partitions, that means, see, if you have an interval AB, how many partitions can you write? You can write any number of partitions. Infinitely many partitions. So you collect all those partitions and name it as phi of AB. Just this is a notation. That means phi of AB means set of all partitions of closed interval AB. This is an infinite set, uncountably infinite set, because you can write any number of partitions, infinitely many partitions for an interval, right? And next, in this partition, there are subintervals, that is I1. What is the I1? x0, x1, and I2, x1, x2. In general, IR. What is IR? xr minus 1, xr. These are the subintervals, formed by this partition. These are subintervals of what? Subintervals of the main interval, closed AB. And then this is the general interval. If you take the final interval, that is In, to be xn minus 1, xn. This xn is nothing but B and x0 is nothing but A. And we also defined delta 1. What is delta 1? Length of I1. So what is the length of I1? That is nothing but it is denoted by mod I1, or its value is x1 minus x0. Similarly, delta 2 is equal to mod I2, its value is x2 minus x1. And in general, any general interval IR, its length is delta r, denoted by delta r, and mod IR is nothing but XR minus 1. Length of any interval is nothing but the difference between two endpoints. Okay. Similarly, what is delta n? Delta n is nothing but length of the last interval in, and that is nothing but xn minus 1. Okay. And this is what we have learned, and some more things. Okay, then after defining this, okay, and we have already taken M1. What is M1? Infimum of f of x. Infimum of f of x on I1, where x belongs to I1. Okay, similarly, what is capital M1? Capital M1 is supremum of the function f of x. Okay, x belongs to I1. That means on the same interval I1, small m1 is infimum and capital M1 is supremum. Okay, in general, okay, small mr is infimum on the ith interval, infimum of f of x, okay, on rth interval, general interval, okay, IR, and capital MR is, okay, supremum of this function f of x, okay, in the interval x belongs to IR. Right. After this, what we have defined is LPF and UPF. Okay. What is LPF? LPF is nothing but LPF is called lower Riemann sum. What is this? Lower Riemann sum. Okay. This is lower Riemann sum, and this can be found using the formula. Okay, summation r is equal to 1 to n mr delta r. That means m1 delta 1 plus m2 delta 2 plus so on plus mn delta n. We have worked out some problems to compute LPF also. Similarly, what is UPF? The UPF is nothing but, okay, it is called as, okay, upper Riemann sum. What is this? Upper Riemann sum. Okay, and this can be computed using the formula summation capital MR delta R, R is equal to 1 to n. Okay, you know that MR is supremum on the rth subinterval. Okay, so that is nothing but capital M1 delta 1 plus so on plus capital Mn delta n. Okay, this is what. And most importantly, we observed that, okay, for any partition P of closed interval AB, always the upper Riemann sum is more than lower Riemann sum. Okay, because upper Riemann sum is nothing but an approximation of the original integral a to b f of x dx, that is area under the curve f of x and above the x-axis. Okay, so this, okay, upper Riemann sum is an approximation. Similarly, lower Riemann sum is also an approximation. But upper Riemann sum is an approximation taken from the above, and lower Riemann sum is an approximation of this integral taken from the below. That is why always we observe, okay, upper Riemann sum is always greater than or equal to lower Riemann sum. Okay. Now further, okay, after defining lower Riemann sum and upper Riemann sum, we have defined lower Riemann integral. Lower Riemann integral. Okay, denoted by integral a to b f of x dx. Okay, underline a, that indicates lower Riemann integral. This is nothing but supremum of all lower Riemann sums. That is, lower Riemann sum is approximation from below. That is why this is always smaller than original integral a to b f of x dx value. So what we are taking is, we are taking maximum or biggest among all small values. Okay, so P is any partition. I write like this. P belongs to phi of AB. I already told you phi of AB means set of all partitions. P is one of the partition. You take any partition and find LPF, and you calculate all LPFs for each partition P. Then you take maximum or supremum among all LPFs. That is nothing but lower Riemann integral. Similarly, upper Riemann integral. So it is denoted by a to b f of x dx. Okay, again underline here, or sometimes some people do it like here. Okay, a to b f of x dx. Okay, this is called upper Riemann integral. Upper Riemann integral. Now a to b f of x dx is nothing but infimum, that is smallest among all approximations UPF from above. Okay, P belongs to phi of A. Okay, now for any partition we have UPF is greater than or equal to LPF. So upper Riemann sum is always greater than or equal to lower Riemann sum. Therefore, the lowest upper Riemann sum is also more than the biggest lower Riemann sum. I repeat, అంటే UPF లో అన్నిటికంటే చిన్న తీసుకున్నా సరే అది కూడా ఓకే, LPF లో అన్నిటికంటే పెద్ద తీసుకున్నా దానికంటే పెద్దదే ఉంటుంది. దట్ మీన్స్ ఓకే, ఈ UPF అన్నిటికన్నా చిన్నది అప్పర్ రీమాన్ ఇంటిగ్రల్. ఈ లోవర్ రీమాన్ సమ్స్ అన్నిటిలో పెద్దది ఓకే lower Riemann sum, but always the upper Riemann sum is more than lower Riemann sum. Of course, this can be proved as a simple theorem or small result. Okay, but now we are not going to prove this here. Okay, but okay, please remember, okay, for the future purpose. Okay, so always remember upper Riemann sum is more than lower Riemann sum. And again, upper Riemann integral is more than lower Riemann integral. It is always there. Okay, and moreover, also remember this definition. Okay, lower Riemann integral is supremum of all lower Riemann sums, and upper Riemann sum is infimum of all upper Riemann sums. That means maximum or biggest among all lower Riemann sums is lower Riemann integral. Infimum, that is smallest among all upper Riemann sums is your upper Riemann integral. And when we from the definition, that is f is Riemann integrable whenever the f is said to be Riemann integrable, and we write it like this. Please remember this notation. F belongs to R of AB. Okay, I think I did not introduce it in the previous videos. So f belongs to R of AB means f is Riemann integrable. That means integral a to b f of x dx exists. Okay, when do you say that f is Riemann integrable? If okay, upper Riemann integral value and lower Riemann integral value are equal, then we say that okay, f is Riemann integrable on closed interval AB. F is Riemann integrable on closed interval AB, and in this case, both the integrals, that is upper Riemann integral and lower Riemann integral are same, and that is nothing but our a to b f of x dx. Okay, if they are not same, that is upper Riemann integral and lower Riemann integral are not equal, then we say that okay, f is not Riemann integrable. F is not Riemann integrable. We write it like this. Okay, that means RAB means set of all Riemann integrable functions on AB. F is also one among them. Then we write f belongs to R of AB. That is, f is also Riemann integrable on the interval AB. If f is not Riemann integrable, then we write it like this. So it means upper Riemann sum and Riemann integral. Okay, upper Riemann integral and lower Riemann integral both are not same or not equal. Okay, if they are equal, then we say that f is Riemann integrable. And further, some more concepts I want to introduce. Okay, now the further concepts which we require in the future theorems is norm. Okay, we have already defined the norm of a partition. What is norm of a partition? Norm of a partition is nothing but the partition P divides the entire interval closed AB. Partition means partition of a closed interval. Okay, divide the partition closed interval into so many intervals. Okay, this is general interval. Okay, this is final xn and this is x0, right? Like this, and this is interval. Okay, and we also discussed the lengths delta 1, delta 2, delta n. Then norm is nothing but maximum of, okay, the lengths of the intervals, that is delta 1, delta 2, so on, delta n. What are delta 1, delta 2, delta n? We have already introduced it. Okay, the length of first interval is delta 1, length of second interval is delta 2, that is nothing but x2 minus x1, and general interval xr minus 1 is denoted by delta r, and finally, okay, the last interval length, that is in interval length, is xn minus 1, that is denoted by delta n. You take maximum among all the lengths. And we are taking the length of biggest interval. అంటే ఈ ఇంటర్వెల్ సబ్ ఇంటర్వెల్స్ అన్నిట్లో ఏది పెద్ద ఇంటర్వెల్ లో దాని లెంత్ ని మనం ఏమంటాం నార్మ్ p. Okay, and one more thing, p1, if p1 is subset of p2, then p2 is called refinement. What do you call? Refinement of the partition. Okay, here also there are three important points of the partition P1. That means P2 has more points than P1. That means P2 contains all the points of P1. Remember, subset means it doesn't mean that it has 5 points, it has 10 points, then P2 cannot be called as refinement. Subset means first, whatever 5 points P1 contains, the same 5 points also are in P2, but P2 has some more extra points than P1. That means P2 contains all the points of P1 and some more points, okay, which are not in P1. Then P1 is subset of P2. In that case, P2 is refinement. In this case, norm P2 is smaller than norm P1. That means if the set contains more points, means you have some more points, okay, in this interval. When some more points are added, the intervals become smaller and smaller. That is why the lengths of the intervals also smaller. Therefore, maximum among the lengths is also become smaller. That is why norm P2 is less than norm P1. This is the first point. Okay, and the second point, okay, if P2 is refinement of P1, then U P2F, okay, is smaller than UP1F. Okay, what is this UPF? UPF is upper Riemann sum. It is a crude approximation of, or an approximation of integral a to b f of x dx from above. And when you increase the number of points in the interval, what happens? It will give better approximation or more closer value to this integral. Therefore, the value comes down when you increase the number of points. We have already discussed it at length. Okay, therefore UP2F is always less than or equal to UP1F, where P2 is more partition. అంటే ఎక్కువ పాయింట్స్ ఉన్న పార్టీషన్ కి తక్కువ UPF వస్తుంది. Okay, and in case of lower Riemann sum, okay, it got reversed. Okay, this is greater than or equal to UP1F. Means what? If you increase the number of points, okay, I'm sorry, this is, okay, this is also lower Riemann sum. So if you increase the number of points in the partition, then what happens? The lower Riemann sum also increases, because lower Riemann sum is an approximation of this from below. So what we do is we take a rough approximation or crude approximation and gradually improve it with respect to the improvement or fineness of the partition. అంటే పార్టీషన్ లో పాయింట్స్ పెంచుకుంటూ వెళ్తూ, అంటే ఇంటర్వెల్ ని ఇంకా చిన్న పార్ట్ల కింద డివైడ్ చేసుకుంటూ వెళ్తే లోవర్ రిమాన్ సమ్ ఏమో పెరుగుతూ వస్తుంది. దట్ ఈస్ వాట్ వి రైట్ హియర్, దట్ ఈస్ ఇన్ఈక్వాలిటీ 3. బట్ అప్పర్ రిమాన్ సమ్ తగ్గుతూ వస్తుంది, దట్ ఈస్ మీన్ బై 2. ఇవి బండగా బై హార్ట్ చేసి గుర్తుపెట్టుకునే కన్నా మనం చెప్పిన కాన్సెప్ట్ అర్థం చేసుకుని గుర్తుపెట్టుకోవడం చాలా ఈజీ. సో ఫైనల్లీ వాట్ యూ హ్యావ్ టు రిమెంబర్ ఇస్, ఓకే, మీరు ఎక్కువ పాయింట్స్ తీసుకుంటే అది ఫైనల్ పార్టీషన్. ఎక్కువ పాయింట్స్ తీసుకుంటే అంటే దేంట్లో ఏబి మధ్యలో, అప్పుడు మీకు యూపీఎఫ్ వాల్యూ తగ్గుతూ వస్తుంది. కాబట్టి యూపీ2ఎఫ్ స్మాల్, యూపీ1ఎఫ్ బిగ్. బట్ లోవర్ రిమాన్ సమ్ పెరుగుతూ వస్తుంది. కాబట్టి యూపీ2ఎఫ్ ఈజ్ బిగ్ అండ్ ఎల్పీ1ఎఫ్ ఈజ్ స్మాల్. ఓకే, అండ్ moreover what other points we need? Okay, okay, you know that P, suppose if P is equal to P1 union P2, okay, then this P is common refinement for P1 as well as P2. It contains P1, that is P1 is subset of P2, P1 union P2, and P1 and P2 are any two partitions. Okay, then P1 union P2 is a common refinement for both P1 and P2. Okay, this is just a note point. Okay, and there is also a small notation called WPF. What is WPF? WPF is nothing but UPF minus LPF. That is the difference. WPF, please remember this. WPF is nothing but the difference between upper Riemann sum and lower Riemann sum for a particular partition. For a particular partition, P is fixed here. So take a partition, find UPF, find LPF, find the difference. That is nothing but WPF. Okay, right. Now we have a small result, but we are not going to prove that result. But this is helpful. So what I said here is, if P2 has more points, refinement means P2 has more points than P1, then UPF is smaller, UP2F is smaller than UP1F, and LP2F is bigger than LP1F. Suppose, okay, suppose P2 లో P1 కంటే ఒక K పాయింట్స్ ఎక్కువ ఉన్నాయి అనుకోండి. అంటే ఏంటి, సపోజ్ P1 లో ఓకే ఏదో A is equal to x0, x1, so on, xn is equal to b. So total, okay, n plus 1 points. Suppose P2 లో ఇంకా కొంచెం ఎక్కువ ఉన్నాయి అనుకోండి, అంటే ఏ బిల్ కాకుండా ఓకే ఎక్స్ట్రాగా ఇంకా ఎక్కువ పాయింట్స్ ఉన్నాయి. సపోజ్ ఒక 3 పాయింట్స్ ఉన్నాయి, అంటే ఫర్ ఎగ్జాంపుల్ A is equal to x0, x1, so on, xn. ఓకే, ఇంకా 3 పాయింట్స్ ఎక్కువ కాబట్టి xn plus 1, xn plus 2, xn plus 3. Then last value is b. Okay, if P2 has more points, how many more points? 3 more points. Okay, then I will give you a rough an estimation for the difference between these two and also the difference between these two. అంటే ఈ UP2F తక్కువ ఉంటుంది అనుకున్నాం కదా, ఎంత తక్కువ ఉంటుంది, లేదా ఇది ఎంత ఎక్కువ ఉంటుంది. అలాగే LP2F ఎక్కువ ఉంటుంది అనుకున్నాం కదా, పెద్దది ఉంటుంది అనుకున్నాం కదా, ఇది ఎంత ఎక్కువ ఉంటుంది. అంటే ఇక్కడ నెంబర్ ఆఫ్ పాయింట్స్ పెరిగే కొద్ది ఎంత ఎక్కువ ఉంటుందో మనం చెప్తాం. ఓకే, ఆ రఫ్ ఎస్టిమేషన్ మనం ఇక్కడ వాడుకుందాం, ఎందుకంటే దిస్ ఈస్ వెరీ ఇంపార్టెంట్ ఫర్ proving the Darboux theorem. Okay, if P1 is subset of P2, that means what? P2 is a refinement of P1, and refinement means what? P2 contains more points than P1. How many points? And suppose P2 contains, okay, how many more points? K points more than P1. Okay, then what you know? Because P2 is refinement, you know that upper Riemann sum for P2 is smaller than upper Riemann sum for P1. So how much smaller? Okay, this is the estimation. See here, UP1F minus UP2F is less than or equal to 2m k into norm P. Okay, norm P1, for example. Okay, similarly, okay, L P2F. Okay, when P2 is refinement to P1, then LP2F is more big than LP1F. Okay, this is also less than or equal to 2mk into norm P1. Okay, right. So norm P1. Now see here. Here I have used this m. K you know. And you know what I mean by norm P1. Right? So what do you mean by m? Here m is nothing but supremum of f of x. Okay? Because when I talk about the integral a to b f of x dx, always we consider this f of x is bounded function. Bounded function means upper bound and lower bound exist. When upper bound exists, supremum also exists. So therefore, this supremum of f of x also exists on closed interval ab, and that supremum, that is maximum value. Okay, roughly saying, maximum value of f of x is capital M. That is this. Okay, so here I am not only saying that up1f is bigger than up2f, but how much bigger I am giving. Similarly, I am not only saying, okay, LP2f is bigger, okay, than LP1f, but how much bigger? I am giving a rough estimate. Please remember these points, okay? We shall use them in the Darboux theorem, okay?